In this video we will develop a range of statistics associated with the linear regression calculation. We start with a data set which gives the experimental y values for associated x values, and these have been plotted on this xy graph. We can start the analysis with the trivial calculation of counting the number of data pairs just by using the Excel count function and defining the cells over which we're counting. So we have 5 data pairs, and then in C8 we can use the slope function of Excel to calculate the slope of the best fit straight line. And for the slope function we need the known y values, comma, and the known x values, giving us a best fit slope of 1.656. Similarly, we can calculate the best fit intercept value, known y's and known x's. So our best fit straight line has a slope of 1.656 and an intercept of 2.782, and we can plot this on our graph by selecting to add the trend line, and we will display the equation on the chart so we can see our best fit straight line with the equation y equals 1.656x for the slope plus 2.782 for the intercept. Now, for each x value, we will calculate the value of y dash, which is the y value on the best fit straight line for that x value. For the first data value, we will be calculating the value of y dash on the trend line corresponding to the same x value as the first data point. And to do that, we will use the straight line equation y equals mx plus c, with the slope multiplying the x value, which is in B2, and then plus the intercept value, which is in C9. So at the value of x equals 12, the experimental x value was 28, and the y value of the best fit straight line, y dash, is 22.65. And we will calculate these best fit values for all of the data points by copying this function down, but so that we do not change the row values for the references for slope and intercept, we will put a $sign in front of 8 for C8 and a $sign in front of 9 for C9, and we can then copy this equation down so we have the y dash values for every value of x. The vertical difference between the experimental and the best fit value is called the residual, and we will calculate the residuals just by taking the difference between the y dash value and the experimental y value, and we can copy that same calculation to all of the data points. The simple sum of the residuals will be 0, with the negative values cancelling out positive values. So to get an overall measure of the residual differences, we will square each residual, the value of the residual to the power of 2, up arrow 2, and then copy this calculation for all the other data points, and then the sum of the squares of residuals is an important measure of the uncertainty within the data. We can now proceed to derive the statistics of the analysis of variance calculation, which tests whether the best fit straight line has a slope which is significantly different from the null hypothesis of a randomly generated horizontal line with a slope of 0. To start with, we will look at the degrees of freedom in the different elements of the calculation. We started off with 5 pieces of information for the 5 data points. For sample data, one piece of information is used in calculating mean values, leaving, in this case, 5 minus 1, or 4 pieces of information, 4 degrees of freedom, for analysing the variability within the data. 1 degree of freedom is then used for regression, leaving 3 degrees of freedom related to the uncertainty given by the residuals in the data. The next step is to look at the sums of squares in the calculations, which identifies the different sources of variability within the data. The total sums of squares is given by the variability in the y values, which we have as the variance of all the y values between C2 and C6, but we need to multiply by the degrees of freedom that are left in the analysis, which is 4. So this gives out the total sums of squares. We have calculated the sums of squares in the residuals in F7, so we can just copy this value into D13. And the difference between these sums of squares is the sums of squares related to the regression calculation, which will equal the total minus the residual sums of squares. And now the mean square values for both regression and residuals can be calculated by dividing the relevant sums of squares by the appropriate degrees of freedom and copying this formula down for the residuals. So we have the mean square values associated with the regression calculation and with the uncertainty in the data given by the residual mean square. The F value now is the ratio of these two mean square values, the regression divided by the residual mean square values. If there was no significant slope in this data set, then the mean square regression values would only have a randomly generated value which would not be significantly greater than the residual mean square values, so the F value would be small. So a large F value indicates a true linear relationship between y and x, and we can calculate the p-value, which gives the probability that an apparently large F value could have occurred by chance. And this is obtained by using the F distribution equals F distribution and using the one-tailed upper or right-hand probability of the F distribution. And for that we need the value of F and then the degrees of freedom for the regression calculation and then the degrees of freedom for the residuals, giving a p-value of 0.017. In this case, this p-value shows that the probability of a non-zero slope occurring by chance is only 1.7%, which is sufficiently low for us to accept that there is indeed a true linear relationship between the y values and the x values. The next step is to look at the correlation coefficients, and the coefficient of determination r squared is a measure of how much of the variation in the y values can be predicted by the variation in the x values and can be calculated as being equal to 1 minus the sums of squares of residuals divided by the total sums of squares. The Pearson's correlation coefficient is then just the square root of this value, so that's the square root of r squared of 0.9413. We could also calculate this correlation directly using the Correll or Pearson's function. For example, we could enter Correll and the two sets of data values, the y values, comma, and the x values, and this would return the same value. We can now perform a hypothesis test to test whether this correlation coefficient shows a true correlation or whether the non-zero value has occurred by chance. And we first calculate a t-value in G16 by using the equation which we have here in the function bar. We can calculate the probability p-value associated with this t-value by using the two-tailed t distribution, and we need the t-value, which is in G16, and then the appropriate number of degrees of freedom in this case, which is the initial number of degrees of freedom in C7, but we have previously now used up 2 degrees of freedom, giving us C7 minus 2, which gives us a p-value of 0.017, and not surprisingly, this gives us the same p-value as the ANOVA analysis, because both analyses are testing whether the slope of the best fit straight line is significantly different from 0. Finally, we calculate some uncertainty values. The standard error of regression is calculated most easily using the XL function, STEYX, and entering the known y values and the known x values, and is the best estimate for the standard deviation of individual values around the best fit straight line. We can then calculate the uncertainties in both slope and intercept. And for example, for the standard error of the slope, we divide the standard error of regression by the square root of the sums of squares of the x variation, which we get by taking the variance of the x values and multiplied by the number of values minus 1, C5 minus 1, and then to convert this into a confidence deviation of the slope, we take the standard error and we multiply by the relevant t-value, which will be the probability of 0.05 for a 95% confidence interval, degrees of freedom in this regression calculation now, which will be the original number of data values, but in this case minus 2, giving us the confidence deviation in the slope.